So today we're going to be having a conversation that centers around, the future of data centers, data infrastructure, the movement of communication, and security as a whole for our infrastructure. Most of this conversation has been discussed over a period of 20 years, specifically surrounding, the security of wired infrastructure, cabling, and of course, data center security, tied to EMP, EMI, as well as the future of what that means, and tied, of course, to green infrastructure. So what I mean by green infrastructure is we're also going to have a conversation surrounding, the use of this new technology that was created by Brett Robinson here and Sentinel Connectors together in partnership to develop the future and the direction of this incredible defined discussion for our business and as well as our security. So Brett, I've got a couple questions for you to start. One of the questions, of course, in regards to not only the design but really functionally just the importance of what we're doing in terms of EMI, EMP protection, especially surrounding data centers, data infrastructure, edge technology. I mean, it really moves to that whole communication path. So can you give me kind of just a general concept in regards to that?
All in one statement?
One statement would be great.
Okay, well, the technology we're using now is totally different than it's been used in the past. In the past, they basically, let's just start talking about jacks for a second. In the past, they'd had jacks filled with transformers. And in the old days, if we're going back to the 80s and 70s, all the way up to the 50s, in the lower frequencies, it was important to do so. There was so much EMI noise at the time, they could hardly get data through it. The trouble with that is they're trying to use technology that was designed really in the 60s and 70s to be used today. The trouble with that data, that connector is that those transformers take a tremendous amount of power. And on the board, you have to put these ASICs, which are basically, power amplifiers. You have to balance them with balance because they're not balanced. And the best you're hoping you're going to get out of it is maybe 300 megahertz. But while you're doing that, you're wasting a ton of power. About $5 million a day just to light these all up and keep them going. Now, what we've done is we've taken and designed the jack with strip line. Now, it gets confused a lot of time with microstrip. Microstrip is basically a one-layer board with a ground plane and a bunch of caps and inductors and what have you. That's not strip line. Strip line, heck, I started doing strip line in the 70s for General Dynamics when we were designing search and track antennas. It was originally designed in '57 by Ma Bell. And the problem they didn't continue with it was they just didn't have the infrastructure. They didn't have the equipment. They knew it worked. They just didn't have the ability at the time to really take it to the next level. What we've done is taken it to the next level. So I treat the jack as if it was a radar antenna, to make it simple. And with the shapes that I build between two ground planes, that becomes an LCR circuit, which means it's always a standard, it's always the same, no matter what you do. There's no components to break, there's no components to overheat. You don't need transformers, you don't need amplifiers, because it is truly the path of least resistance. And if you remove that path and allow transmission data to go through and power to go through, well, you're not using up millions of dollars in power. On the same thing.
So that applies to the green factor.
That applies to the green factor.
Right.
Now for EMP, it's not the end-all be-all to EMP, electromagnetic pulse, but EMP, since there's no components, EMP doesn't bother it, so it's immune to it, which means anything on its path behind it isn't bothered by it as well, as long as you keep to the same type of technology. As soon as you add in amplifiers and other things, well, then you're defeating what you're trying to do. On the other hand, They make high-speed data transient voltage suppression devices, which we call avalanche diodes. And one end would go to the line, the other end goes to earth ground, and when the larger transients come in, whether it's lightning or EMP or any kind of RFI, it gets, as soon as there's an over voltage, it shunts and shunts it to ground. The great part about it is that TVSs don't blow short, where MOVs and other older systems, it's 100% of the time they blow short. Now, I don't mind if they blow open because it opens the line up, which prevents energy, again, from entering into a place where you don't want it to go.
Exactly.
But if you short, it's going to go to places you never wanted it to go to, and now you have bigger problems.
And that's exactly what we're facing in the current infrastructure.
Right.
Right. And so on that same path, right? So the big question is, what is this going to what is the roadmap to something like this? I mean, what do you see as what needs to happen from the standpoint of, step by step, from the standpoint of deploying?
Well, from the standpoint, unfortunately, people are going to have to realize what they have isn't going to cut it.
Right.
There's always been a requirement for EMP. There's always been a requirement for EMI. There's always been a requirement for RFI compatibility, but it gets in the way of profit. So the TIA and the IEEE are a big case of that, where they were more interested in what the companies that were backing them than the truth about what had to be done. So in this case, we're having to look at not only the connectors, but the plugs, the cables, the shielding. We're having to look at how the boards are relayed out. All of them have to follow the path of least resistance. You can't use FR4 anymore. That's a thing of the past. It's 200 ohms. There is materials out there where instead of using fiberglass, they use Teflon, which is called a femto material, less than zero. Now that allows you to go fast. That allows your same copper lines to work. Also, you need to get away from gold. First of all, gold is getting too expensive to deal with, even 10 karat gold. And the truth is that sterling silver, or commonly known as German silver, is actually better on a path on your lines and what have you for transmission lines, especially if you want to go above 10 gigahertz. If you want to go into the terahertz, you can't transmit it over gold. Gold, the resistivity is just too high, and the reason being is the fact that the gold that they use today is very brittle. It's 10 karat. Generally, it's mixed with all sorts of other amalgamates that they've dumped into it, nickel, they've dumped bronze, and they make this mash that they call gold. So now it's highly resistive and mildly conductive. So what you want it to be is no resistance and very conductive.
So on that point, I think that one of the challenges in really presenting this as an option for the future, we have to know that it's going to cost money to do it. There's no other way around it.
It's a big one-time cost.
It's a big one. But so this is what I want to clarify that, because I think the audience really needs to pay attention to some of the numbers that we pulled in regards to cost efficiencies. So part of it is one-time costs, right? And we know that with the infrastructure spending bill, and we know that we have to get better at this. And there might be some government support, and that's definitely around the corner. But I think the cost saving is what's fascinating. If you look at some of the cost savings in regards to some of the numbers we've received, so energy consumption cost per watt, right, per hour. I think that we did some initial studies. Basic data center cost per hour is approximately $26,495 per hour per 1 kilowatt hour on the average, right?
Yep.
And what you found is a Hawaii data center spends approximately $3,290 per 1 kilowatt hour. So Berkeley Data Center, approximately 70 billion kilowatt hours a year, or 5,833,333 kilowatt hours per month. So
that's the students all,
and that's all the students on the computer, right? So roadmap for success. So I have here the amazing differences in the reduction in costs, and you found that what was it, about 80% reduction?
75 to 80% reduction in cost because you have the path of least resistance. They've been spending millions of dollars daily on an old infrastructure that is costing them millions, and yet it wouldn't cost them millions to redo the infrastructure and do it the right way. In an example, I got a phone call from one of the companies, and he says, I'm having a problem, and I was told to talk to you. And I said, okay, what's the problem? He said, well, I'm using MagJack. I said, fine. Well, what's the problem? He said, well, I'm only at 100 megahertz. I said, okay, that's perfect for 100 megahertz. He said, but we needed to make it go further, so we started increasing the amplifier. And as we increased the amplifier, I said, your data started to drop down, and then your connector melted? And he went, yeah. I said, well, that's because you've taken the transforms on the inside, you've saturated them, and now they're glowing like light bulbs. And what's happened is they're getting so hot, they're expending so much heat, so much calories, they're literally melting the MagJack. Oh, so that would be a bad idea. Yes. And I said, where you should have been using CAT6 or CAT6A, we're using CAT5E cables. Well, they're old cables, so they're CAT5E. Well, they weren't designed for you to put this kind of power down them. You're only looking at 28 gauge wire. So that wire is very resistive, and it's what we call it the big R, and it's pushing back like a resistor. What you're supposed to be using is larger gauge wire, and the bigger the better, and the path of least resistance goes down, your R goes down. Now you're transmitting at the data you wanted to transmit at, and you're not heating up your cables. He says, could you talk to my management about that? I said, I'll be glad to talk to them, but here's the big deal. They're going to have to realize they have to change the way they think. If they don't, they're not going to move any further on. And you have requirements, especially putting this in aircraft, that your requirements are that you have to meet EMP, EMI, and RFI. You also have to meet radiated susceptibility of greater than 200 volts per meter. Yeah, well, you can't do it the way you're going.
Right.
Your boards are going to melt.
And so that's one of the things that really excited me, obviously, about where we're going with this is the fact not only are we reducing the cost via the use of say, power to support, air conditioning and cooling systems for these larger data centers, as well as any of the systems that are out there, is that you're also increasing data. The pass-through.
Oh, your pass-through is just increasing
fundamentally,
right?
Yeah, and that's one of the fascinating parts about all this. I mean, I can't have found more of a win-win-win, and knowing full well there's a cost to begin with, but the reduction that we're seeing in terms of not only productivity over the actual data, the lowering of costs based on the heat transition, and the EMI and EMP, satisfaction.
Well, first of all, they have to meet those, whether they're commercial or military.
Right.
The companies we deal with in Germany and Israel, everything they design a commercial product to meet the military standard. And the reason being is now they can sell a commercial product to the military without having to spend hundreds of thousands of dollars on testing and then going back and redoing it. So they try to do it right the first time. I'm not saying they're perfect, not even remotely. I'm saying this, they realize that they have a problem and they have to meet their obligations. If you don't change the circuit boards, if you don't change the materials you're using, if you don't change how your cable shielding is, where the cable shielding is actually working as a cable shield, and you don't think that the cable shields just magically absorb energy, because they don't, then you have to start looking at the whole system, the whole ecosystem, and decide what it's going to take to make it work right, especially as you want to go in higher speeds. As you get to going to the higher speeds, shielding becomes a critical factor.
That's right.
Not shielding, letting things float, you can't pass. We get people to send us stuff from UL all the time. We test them here in the lab. And I said, you didn't hook up the shields. Well, we were told by Company X that you didn't have to. Right, but Company X just got pulled off all the aircraft And the reason they got pulled off their aircraft and got pulled off their cars, and they got pulled off all their other stuff, is because what they told you was 100% not right. It's right for them because they only want to sell you what they have. But the truth is, you've now installed something that's never going to meet your requirements. So I asked one of the guys, I said, let me ask you, if it's absorbing the energy, these shields, where does it go? He goes, what do you mean, where does it go? I said, where does it go? He says, well, it dissipates.
Right.
To where?
To where? Bleed.
Yeah, where does it go?
Yeah.
It has to have a path out.
Right.
Oh, it goes out into the ether. No, that doesn't work like that because now you have EMI. So he said, well, where does it go? I said, if you don't have a path to ground, earth ground.
Right.
He says, all we have is chassis. Okay, so you go from chassis to earth, which is, if you look at anything, whether it's commercial or military, that's how you have to do it. It has to eventually go to ground, right. Earth ground. If you don't have earth ground, then it has to go to minus VDC, the negative side of a battery, just like in your car. Because your car sure doesn't have a little wire hanging on the ground that you're dragging down the street, right? And he went, well, how come they didn't tell us that? You know what? I can't speak for them. I can make assumptions, but I'm telling you the truth, what has to be done.
So part of the most important pieces of this conversation, not only in regards to current political circumstances in Europe, but also to the fact that our data infrastructure was created over 35 years ago to support systems that were really pushing a quarter of what we're now pushing through those data centers.
Oh, it was even less than that.
Less than that, probably.
I remember working at General Dynamics in the 70s. I was designing search and track antennas. And, they thought 100 kilohertz was ooh baby. Today we're looking at gigahertz and terahertz. That wasn't even a concept I could have considered. We knew what the words, the terminology was, but at the time we couldn't even conceive a concept of how we would get there from here.
Yeah, and so we're looking really, we're pushing 50, 100 gigs through this.
Oh yeah, we're doing 25, 50, and 100 gig through the CAT8 jacks we have now.
And that tells you a lot, ladies and gentlemen. This is really what the future is. I think that putting this together as an entire process, you're really focusing on the future of what the infrastructure is going to look like within the next few years. I believe truly, based on my research and all the work that we've done with many of the we'll say end users and consultants in this industry, is that this transformative period is going to result in a change. And I think that it's either we do it now or we're going to pay the consequences.
Well, here's the bigger worry you have to worry about. And I talk about EMP, and guy goes, oh, we've been told it's no big deal. So I said, here's how it really works. You have a 100 megaton bomb. You put it 1 mile above the United States. You don't really want to blow up the United States. You don't want to kill anybody. But what you do when it explodes, it creates a thing called a Compton effect. And the Compton effect is these ions are spinning faster and faster and faster. So kind of think of it as lightning on steroids. It comes down, it doesn't bother humans. We don't feel it, we can't touch it. But your equipment burns up. So basically you can turn the United States of America, because you haven't taken care of your infrastructure like you were supposed to. You push us into the back ages where there's no phones, there's no cars, because everything is working. The only thing that might work is your 57 Chevy, because there's nothing in it to burn out. It likes, with the coil it's got, it likes it.
And it really helps the electrical cars out there. So part of this green movement, right, there's nothing wrong with the concept, but to really make it work, there's a lot that has to happen. And with that in mind, I think the challenges that we're going to face is really getting this to the marketplace in a way that specifies the use of this technology in the appropriate way. Robinson Engineering and Sentinel Connectors have come together to really bring something very unique to the industry. And the reality is that with the experience and really the background of these gentlemen, they've been able to really come together and do a great job to bring a product and technology that can be adaptive. Now, the reality is, of course, is that it takes a community to work together, and that's what we're looking for. We're looking for the engineers, we're looking for the government. We're looking for corporations to really understand why this is so important. This isn't a call to arms, but it kind of is. And part of it is that just really understanding that if we're going to really protect our infrastructure, roads are important. Don't get me wrong. I believe in that like anyone else. But if we don't take care of our data infrastructure, our infrastructure to support this 78 billion devices at the edge that are now in the marketplace, to realize that every person holds a phone in their hand that could be terminated by one potential EMP strike by, say, a foreign adversary. The world is not a safe place. We found that out. We have to make a determination. If we're going to protect our systems, we're going to protect our world, we're going to live in a more green pasture in a green world, we're going to have to do what it takes to do it across the board. Thank you very much for this wonderful interview.
What you're looking at here is a demonstration of the MSEC, the Tempest cable, the CAT8 jack, the CAT8 test boards, RFI, radio frequency interference, working as data, being sent down through our chamber and then into this Regol unit where I can then look at the eye coming out of my jack and my plug, and I can look on the spectrum analyzer and be able to see that there's literally no interference coming out of these Tempest cables. So you get to look at 3 or 4 different things at the exact same time to prove that the jack, which is the eye, the plug, which is in the cable, that the shielding and grounding in a grounded chamber, isolation chamber, right, for RF chamber, they're all playing in so that you're actually truly seeing that there's no interference on the spectrum analyzer. All right, so now in this application, what we're doing is we're running a MagJack, a CAT6 non-shielded cable and plug, and we're doing the same test, trying to see, using 5 milliwatts of power, RF power, what is the difference between the green ecosystem and the CAT8 system versus what's out there today. So what we have is, using the MagJack, and because we only have 5 milliwatts of power, we have no eye. And you can see that there's no eye. You can see the scattered RF noise because you've saturated the CAT6 cable without shielding. And if you look on the spectrum analyzer, you will notice that those little humps and squiggles you see are showing you how much energy is being released from the CAT6 cable that has no shielding, and that it's emitting EMI and RFI, electromagnetic interference, and radio frequency interference. So basically, the MagJack, which works at the lower frequencies, can't operate at the same 500 megahertz frequencies in sine wave that the CAT8 jack did. So you're not trying to argue one versus the other. What you're trying to show is why they've been having problems in their data centers, why there's noise, EMI noise, why is there overheating. All of those reasons are why you can see instantly there is no eye. I can't go higher. Now, if I wanted to, and I had an amplifier, I could pump more power down this cable so that I could get a corrupted eye and get a little bit better of a sine wave. But in this case, I can't, because I'm prevented by the architecture that's within the MagJack and the standard off-the-shelf CAT6 unshielded cable. This demonstrates to you that you can't use it for MSEC, you can't use it for Tempest, and why you have to use so much power in data centers just to get data out. So what you're here seeing, we're back in the original configuration where you can see a perfect eye with the CAT8 jacks connectors. You can see them with the Tempest cable, with the Class 1 cable, and you can see how quiet it is on the spectrum analyzer in the back.
Very cool.
This was actually interesting because they were saying for years, you can't tell shielding effectiveness. Well, the military's been doing it for 75 years.
Yeah.